Okay. So the picture looks like this one. Sorry, I should. The notes sometimes leads to error. So I won't, I just leave this one. Okay. All right. So this is a sample of something that's not simple. Okay. So for example, this one's simple. Okay. So in the integral now becomes something that looks like this one here. Okay. This one or this one. dy dx, and the inside integral have a bound in term of function of x. Okay. All right, so the thing is how to switch integration order. Is it possible? So we see that in a rectangle, meaning the all the bounds are constant, both x and y are constant. You can switch order directly, okay, without much considerations. Uh, so let's start with this one. Okay, so let's switch to the textbook. I'll show you some example in the book, and then we'll do some exercise. Okay, here, and let's see what's the trick with this one. Okay, so this one's evaluations. I'll show you the evaluations. In evaluation, for example, this example one. Okay. Okay, so let's integrate over y. So dy, integrate this one, and plug in the bounds x squared and minus x. So the after you integrate with respect to y, all the y will disappear. That leaving you with just x, and then carry out the integrations with respect to x variable. That's what you get. So something that's easy. Okay. Okay. But the important thing is that um, how do we able to recognize area of integrations? Okay. For example, this one. And now the question is how to recognize the take out the to the uh, okay from here. Okay, so in this case, this is actually y equal minus x. This is x equals 3 equals 5. So that is the bound. Okay, so the area of integration is this one here. So y less than minus x squared, and x is between 3 and 5. Okay, so y here is the vertical, from down up, and this one horizontal directions, from left to right. Okay, so what you have from here is uh, first you get to recognize this one, this area, and then plot the graph. So in this case, you have y equals minus x. So minus x is, and y equals x squared. Okay. So between 3 and all right. So the area is now this moving from down to up. This graph to yeah. Okay. And from left to right, moving from 3, 5. Okay. So we have this area now. It's domain of integrations. Okay. So that's how you're able to recognize the domain of integrations. Okay. Let's go for another example. All right. Let's do this one. Okay, so if we domain into integrations, now the questions. Equations. Okay, we see that from here. So this is the x, this is the y. Okay, so x here is from left to right is going by 0 to y squared. So here, oh, I just write it here, 0. Okay. And y is between y equals 0, y equals 1. Okay, so the area looks like this is y1, right? So all right, this is x equals y squared. So x equal y squared is same as y equal square root of x, right? So this is square root of x. This x equals 0. X equals 0 is this. Okay, so you're moving left to right in this direction. Okay. And this is the same as x equals y squared. Okay. This is x equals 0. Then y from 0 to 1. So from 0 to 1. So at the end, you have this as the domain of integration. Okay. All right. So then we carry out the integrations. Okay. Okay. We don't need to. Okay. So let's do the inside. 2y into the x dx. Okay. So everything's in terms of y is a constant with respect to x. So we can move this out. So it's 2y. Okay, so that's easy. Okay, so again we have here 2y e to the y squared minus e to the 0 is 1. There. Okay, so then we carry out the outside integral. So this outside integral is this. Okay, and this one y equal to y squared, which is this one easy because 2y is actually comes from the derivative of y squared. So exactly this derivative of this. So substitutions. This just give you square. This give you y squared. Okay. plug in 0, 1. So you get, let's see what you get here. E to be 1 minus 1. And plug in 0. This is 1. Plug in 0, that's 0. Okay, so minus 1. Okay. So in the end, you have the integral. What is this? 2y e to the okay. Okay, so the thing here is why do we need to recognize the or the graph the domain of integrations? All right, so let's see. Let's go again to this. All right, so let's do example 3. All right. Question so far? Okay. Okay. Okay, now so this one is to compute a volume, find the volume of a tetrahedron bounded by coordinate planes and the planes this one here. Okay. All right, so usually that's in the first octant. Okay, so how you recognize this one? First, let's recognize the plane here. Right? So we usually put that here. All right, so intersection with the let's see, on the x-axis. On the x-axis, the y is 0 and z is 0. Okay, so just put y and z equal 0. So that gives you 3x equals 12. So x equals 4. Okay. Yeah. On the y-axis, or on the y-axis, you see that x and z 0. Okay, so this gives you x and z was 0 to just 6y minus 12, 0. Okay, so y equals 2. Here we get 2. And in the z-axis, you see that the x and y equals 0. So in that case, would be or z minus 0, so z equals. All right. So the tetrahedron is formed by this one. There. So that's the tetrahedron. Okay. So that's the. So how to be able to compute it in volume? Well, in volume, let's see. Let's put this. This is a domain of integrations. Okay, and let's think this is the as the integrand. Okay, so in this case, this is what we call area region T. Okay, so we have volume. Here is the integral over the region T of the. Okay, so let's figure out how I feel here. So here we have a z equals. Okay, so express this in terms of z. Okay, so here we have x plus 6y equals 12. So z is all right, so that's our okay. And the area now is the domain of integrations. See, this is 4. This is 2. So in this case, depend on whatever you like, either dy or dx. Suppose we proceed first vertically. Okay, so this is y directions. Okay, so this vertical. So this y 0. And this is, let's see, how to find this one. Okay, this one comes from this line here. Okay, so this line comes from this equation when z equals 0. When z equals 0, so you have the x plus 6y equals 12. Okay. This is so in terms of y, you should write this down as y equals so divided by this 12. So 2 minus x over 2. Okay. So this is the area of equations. Then the volume Right, so that write this down. Volume would be from x equals 0, y equals 0 to y equals 2 minus x over 2. Okay. And the x varies from 0 to 4. And this is the function. This is the y first, and then the x. Then you can compute this one. Okay, so I'll let you do the detail of computing this one, or just show you the result from this one. Okay, so volume of solids is this one here. And integration, this is exactly what we have. So we have it as before. Okay, questions so far? All right, let's do something else. Okay, I'll just show you. I'll skip the example 3 first. We'll do that later with something easier. We need to switch order of integration. So F this one here. All right. So what's wrong with this this integral, the order? Okay, you see that. So I put note on red. Red notice. This one. Here. All right, so this is if you try to carry out this integral, it's impossible because e to the y squared does not have antiderivative. So you cannot compute this using fundamental theorem of calculus. Fundamental theorem of calculus. Then has no explicit antiderivative. Okay, so it's a dead end. All right. However, if you try to do this one, this would be easy. Why? Because we integrate with respect to x. Okay. So because this is we just x e to the y squared plus c. Okay. So then let's do um, let's do the integration with respect to x first. Okay. So this is the conclusions. Okay. So in switching order integrations, um, this direction means vertical first, then horizontal. Okay. So when you switch order, you have to go horizontal first and then go vertical. Okay. So that then vertical. Okay. So then you have to be able to recognize uh, draw the domain of integrations. Okay. So in this case, let's see. I need the problem again. So let's see. No domain of integration. Okay, so this tells you that y going in this direction. This is the y equals to, okay, and while x is between 0 and 4. Okay, so you have something that looks like y equals x over 2, y equals 2. Okay, so let's draw this one. Y equals, yeah, and y equals 2. Okay, and from 0 to 4. All right, so this is parameter to 4. And x goes from here to here. So you're going from, oh, sorry, from this one here. So this is the area. And then 0 to 4 going in that direction. Right? All right, so now let's draw this in terms of a switch order here. When you switch order, we need another expression. So this expression is the same as x equals to y. Okay. All right. So going switch integrations. When you switch order, x going from left to right. Okay. Left starting from 0 to right. So x equals, in this case, to 1. X equals 0. And y from, now that's easy, y from 0 to 2. Okay, so then the integral becomes, I just say this is in. So our integral now, when you switch order, this becomes, okay, just to remind you what we try to integrate here. Okay, so from 0 to y. Okay. Okay. And here you have e to the y squared now become dx dy. Okay, and um, because this is containing y, and you integrate respect to x, this with goes outside the integral, so you have something like this, e to the y squared, so integral of this is just the x. Okay, let's go, and that's easy. X is just the difference in, okay, so this just give you 2. Here you have just 2y. Oh, sorry. Here you have equal y squared. And this integral gives you just 2y. 2y minus 0. dy. Okay, but this integral now, the integrand, this 2y is exactly the derivative of y squared. Okay. So you have the y squared. Okay, that's what you have. E to the 4 minus the 1 is, okay, so that's a process that you will need to have switching order of integrations. Any questions? All right, so let's do some more examples. So this is just evaluate the integrals. Okay. Get the result. All right, let's do 16, for example. Uh, okay. The integral is easy because it's just x plus y. So you can do integrate with respect to x or with respect to y. It doesn't make any difference. Right? So just the thing is about the bound. So 0, 0. the origin, 0, 4, and 1, 4. Save this one. The scale is not good, but it's all right. There. Okay. And so you need to find the equations now. Okay. So this equation 1, 4 is y equals 4x. Okay. And we find the equation. This is 4, this is 1. Okay. Or you can write this down as same as x equals y over 4. Okay. We may need this. Sorry, let's do this one. Okay. In case you need to. All right. So things from, for example, if you want to do the x first, okay. So the x first is going this direction. Okay, so in this direction, x is from 0 to this equation, x equals y over 4. Okay, and y moving from 0 to 4. Okay, or other directions. If you proceed this way first, so the green one, you see that the y would be goes from this equation y equals 4x to y equals 4. Okay, and the x varies from 0 to 1. Okay, and in this case, the integral would be the x first. So x goes from 0 to y over 4. The y from 0 to 4. And using the formulations, so y first, y goes from here, 4x, 4, from x 0 to 1. That would be the same. Okay, and then you can compute this one. Check whether they are the same thing. Okay. Okay, any questions? All right. Okay. And all right, so let's 20. Let's do 20. Is 20 oh here. Okay, so this is a region between y equals x and y and q. Okay. So here y cube is cube is this. And x equals This one is -1. Okay, so you have two parts. Okay, two parts. This is part 1 and 2. Okay, so then this integral. All right, so let's move from in this part. Okay, so first you want to move, say you want to move this first. Let's make it bigger. Okay. Okay. It's from -1 to 0. So here, x between -1 and 0, y from this x to y equals 2. Okay. So this part, if you move, yeah, like this one. Here, x between 0 and 1, y move from y move from the cube to x. Okay. So then the integral now, a area. All right, so we need to find two areas. Here, see, y comes from x. Here, add the y first, and then the x is from -1 to 0. Okay, plus x dy dx. See, in this case, moving from x cubed to x from 0 to 1. Okay, and you can compute this easily. Okay. So for example, here because you integrate with respect to y, x goes out. And okay, questions? All right, so let's take a short break, 5 minutes.